Welcome to the second part of the lecture on hardware for machine learning. So, in the first part, we discussed the basics of deep learning, as you can see. So, we discussed what a convolutional layer would look like. Because for us, accelerating that is a matter of priority. The rest of the layers are reasonably easy to design in hardware, but the convolutional layer in particular is difficult. So, what we had basically said is that a convolutional layer has k functional units, where a functional unit is nothing but a convolver in a certain sense, right? If there is such a word. So it takes as its input all capital C, C for channel, all capital C input feature maps, IF maps, and then produces an output feature map. Similarly, the same thing is done by all the K, right, capital K functional units to produce capital K output feature maps. So, pretty much what happens is that a convolution is computed between a kernel and a feature map in a given functional unit. So, of course, the kernel is a function of the feature map number and the output number. So, there are CK filters or CK kernels, where a filter and a kernel, these terms will be used interchangeably. So for each IF map, OF map pair, we have a filter kernel pair. So a convolutional layer will take as its inputs capital C IF maps and capital K OF maps, and sorry, it'll take as input capital C IF maps, capital CK filters, and produce K OF maps as output. So given the fact that we were there, let's move forward. So let's look at a convolutional operation mathematically, right? So the key operation was that we select a region in the input feature map. In this case, it's a 3 cross 3 region over here, as you can see. And we have a 3 cross 3 filter. So what we do is that we do a pairwise multiplication, right? So we multiply this element with this with this, right? So you can consider it like a dot product, but it's more like a matrix dot product, right? It's a pairwise multiplication and summation. So then we produce an output pixel, which is the output OF map in this case has exactly the same dimensions as the input feature map. So again, this may not be the case, but let's take the simpler case. Generalizing it for other cases is quite easy. So basically, the output feature map would have exactly the same dimensions. In the output feature map, the value of this pixel, which let's say is given by OHW. Why HW? Because this is the hth row and wth column, right? So basically, the its coordinates are HW. So let's say we have taken the row column format here instead of the x-axis y-axis format. We have taken the row column format where we go with the hth row and the wth column. So OHW, right, which is nothing but the value of the output pixel, is just a summation of the pairwise products. So the summation over here, as you can see, it's not a 1D sum, but it's a 2D sum. So given the fact that it's a 2D sum, we'll have two of these summations, right? There are two axes, so basically you have two summations. And the two iterators are R and S, kind of R for row and S for column. So what we do is that we essentially walk through all the elements in this region and we find the corresponding elements over here, we multiply and we add, which is exactly what we are doing. So I is the input feature map. We start at location HW and we walk through all the elements. So basically the iterators are R and S, right? In a row and column, but in a column would have been a different letters. So let's use R and S. So essentially we look at all values of R and S. So we start with HW. So look at all values of R, we look at W, then we start at all values of S. So essentially we traverse the 2D space and for each point, we multiply it with the corresponding value in the filter, which can again be represented with an R cross S pair. So then we multiply and then we add. So let me clear off the ink over here. That will make life somewhat easier. So basically, the key point is understanding this equation. If you are able to understand this equation, we are good to go. So I would suggest that people who are watching this video not progress beyond this slide unless they are able to understand this equation. And I would like to explain what is over here. So this says that coordinates in the 3 cross 3 filter, which is this one, and the pink window, right? So basically, the idea is that you're giving these are the coordinates in the pink window, and these are the coordinates in the filter. So sorry, this arrow should have been here. And the key point is that we look at one thing, we find its corresponding coordinate over here, of course, with the offset of h and w, and we find the pixel, we multiply and we add across all rows and all columns. So if this part is understood, trust me, we are mostly done. So the basic equation that we have, which is exactly this, right? Which is exactly this. I've just copy pasted it over here, where the value of an output pixel is essentially this thing over here. We know how to interpret it now. So HW is the starting point and R and S are the iterators that we multiply. So this is of course for a single input map. Now let's consider multiple input maps where an IF map is also called a channel, right? An input channel. So now if there are capital C channels, so the terminology that we will use or the notation that we will use, we will have capital C channels where small c is the iterator, right? So small c will essentially vary from 0 to capital C minus 1. So the idea here is that for a single OF map, what we will do is OHW. We will have this equation. Along with that, so what did we see? What we saw over here, I'm sorry, I just go back, is that we compute separate convolutions for each input feature map with its corresponding filter, and we add all of them to produce the final output map, right? So in a certain sense, in this case, of course, we are considering a single input channel. If we have multiple input channels, then this will remain more or less as it is with a small change. I'll tell you what. But this additional summation will come, which is basically saying that we are adding it across all input channels, across all capital C input channels. We are adding them for small c is the iterator. So the only addition that we have two additions. The first addition is that we consider the input feature map for the cth channel, right? So in this case, we have multiple input feature maps. For each one of them, we consider, so IC is nothing but the cth input feature map. Then we do a convolution. And in this case, the filter is different for different input feature maps. So that is why this, of course, was the coordinate within the filter. Filter kernel, same thing. But FC basically means that this is the filter that corresponds to this input feature map. So this is the only addition that we did as compared to this equation. So if you see this equation, the new parts are this and this, which basically is saying that we are specializing the convolution for the cth input feature map and its corresponding kernel. So we do this for all the input feature maps and we add and we get the value of the output feature map, a single output feature map. Now let's say we have multiple output feature maps or OF maps. You have capital K, where again the iterator k, small k, varies from 0 to capital K minus 1. Then in this case, what will happen is what our convolution operation will produce is that it will produce the HWth pixel of the kth output feature map. Again, we don't make any change, right? So we start from this equation. So let me get rid of the writing here. So the key point is that this remains as it is. It is just that now the filter, right? So we will use the filter will change in the sense for every input output feature map pair, because let's again go back to this equation. So what we said is that look, for the kth output feature map, we are again reading all the filters. But again, let's say that it's the small kth output feature map over here. For the cth input feature map, we will use the essentially the c comma kth filter, right? So we have capital ck filters. So we'll use the filter which uniquely corresponds to the input output feature map pair. So this is exactly being encoded in this, in the sense that we are using a filter which is a unique, which is uniquely determined by the input output feature map pair, in the sense if it's the cth input feature map and kth output feature map, both will determine the filter because it's now a 2D space, and the rest of course from here remains the same. So we have gradually complicated this. I will only add one more complication, not more, I promise. So now let's look at it in full glory, in the sense let us also add the effect of multiple images. So what is multiple images? So the idea is that why do you do convolution in the first place, right? So you do it because you have an input image, which is nothing but a 2D matrix. And from that, you basically send it through a deep neural network, a DNN basically, to figure out, many things. Let's say, does it contain the image of an apple or not, or does it look like a car or not, right? So the image is essentially the original input. Then, of course, you create in every layer, you take in a few inputs, you create a few outputs. Again, those outputs are an input to the next layer. Again, you create a few more outputs, so on and so forth. But essentially, this entire thing is happening primarily for an original image. So now what we do is, if we consider multiple images where the iterator for the image is n, then pretty much we will have output feature maps which are now indexed by the image number also. But image is the original input on which we are doing. So if that is the case, the only additional thing, over and above this equation over here, the only change will be an n getting added here for the image number, and filters, etc. Everything remains the same, but the input feature map would now also have an n over here corresponding to the image number. So we have this dirty looking equation over here, but we have systematically derived it, in the sense we have made the number of the image basically parameterize the input output feature map number, and the rest of course remains the same. So this should be reasonably easy to understand. Given the fact that we have gradually built this equation up, the only addition we are doing in this stage is adding these two terms. What this basically means is that we are doing the same operation for different original images, and this is why the input and output feature maps are kind of getting parameterized by the images. So when you say it's for the nth image, you say that all this data is for the nth image. And clearly the filters are not a function of the image. That's the reason n does not appear here. So let's now summarize all our terminology. The main thing is that this table unfortunately needs to be memorized, because we'll be using these variables over and over and over again. And that's the reason, it may be a good idea to memorize this table right here. So let the number of input images or 2D matrices be capital N. So its iterator is small n. The number of input channels for any layer, so this is again layer specific, is capital C, right? C for channel, and its iterator is small c. Again, for a given layer, let the number of OF maps, output feature maps, that we produce be capital K. Its iterator will be small k. And the dimensions of each IF map and OF map we have assumed to be the same, even though in practice it need not be the same, particularly if we do what is called strided access, in the sense that in this case we compute an output pixel for every HW pair, but it could be like every HW pair where H and W are even, right? So in that case, the output feature map would be smaller. But in any case, in output feature map size will always be smaller than input feature map size. But in this case, we have assumed it to be the same, and that's easy to explain. But in case it's smaller, you can easily extend this equation. So the dimensions of the IF maps and OF maps are h cross w, height cross width. Height is the number of rows, width is the number of columns. And the iterators for h and w, capital H and w, are small h and w respectively. And the dimensions of the filter are capital R, capital S, which is small r and small s respectively. If you are considering a batch of capital N images, right, original inputs, each in a layer, each OF map is produced from capital CIF maps, and there is a separate filter for each IF map OF map pair, making a total of these many filters. So what do we have? So we basically take this equation, again a screen clearing is due. So this equation initially could look scary, but we have essentially broken it down. We derive this gradually. So what you can see is that this can be replaced with a piece of code to exactly compute this, right? So in this case, what do? You would iterate all values of H, W, R, S, and C, and N, and so on. So basically, you would have this classic 7 for loop structure. So just count, there are 7 loops. So the outermost loop here loops through the input images. Then we loop through the outputs k, that is small k. Then the input channels. Then H, W, R, and S. In every case, O, N, K, H, W, which is nothing but this value over here, is essentially a summation. That's the reason you have plus equal to. And you assume that this is initialized to 0, of course. Is basically this value, which is nothing but this value over here of NCH plus R W plus S multiplied with its corresponding filter value, which is also given here. So as you can see, this 7 for loops, this is a direct representation of the summation formula that we had in the previous slide. And in this case, what we are doing is that we are simply, looping through all combinations. We are just multiplying and adding. And of course, we are adding for different images and different out, and we are producing capital K output maps for all the capital N images. That's our final output. So the first thing is that you need to convince yourself that this 7 loop structure over here, which, sorry, this 7 loop structure NKCHWRS, right, is nothing but this. And as you can see here, all that we are doing is we are multiplying and adding. So initially we are choosing the image, then we are choosing the output channel, then we are iterating through all the input channels. Then for each input channel, we are kind of iterating through all HW, all the pixels, and for each pixel, we are again iterating through all the through all the elements of the filter, right? So we are doing this. So of course, there is a small catch in this, in the sense there is a small problem, but I will not discuss it now because it will just make things complex. But there's a small problem and an easier fix, and a very easy fix. But I'll come to that later. But the key point is that this is a classic 7 loop structure that you are seeing over here, and this is just a sum of products. And here is the fun part, that each of these partial products, right, can be computed independently. There is no problem. So there is a lot of parallelism in this computation, in the sense you can reorder the loops. It will remain exactly the same. In fact, you can reorder these loops any way that you want. This computation will remain exactly the same, right? And also, you can do all of them in parallel and then add them. It would remain the same. So you need to kind of convince yourselves of these things. It is easy for me to state that a loop, any of these loops can be reordered and no change will happen. But to actually appreciate that would take some amount of thinking, and I'll not kind of take away the opportunity of thinking from you. You people need to think and genuinely convince yourselves that this is indeed the case. So now let's look at, broadly speaking, where we are, right? So we have the 7 loop structure over here, and then I claim that each of these are independent computations, so the loops etc. can be reordered without any problem. And our input for a given image is essentially capital CIF maps, each with dimension HW. Then we have capital CK filters with dimension RS, and our output is KOF maps with dimensions HW. So now for a given input image, you can have, of course, hundreds of layers, but then you can have several convolutional units in a layer, as you can see. Then we could also have the other layers that we discussed, like ReLU layers, pooling layers, other convolutional layers, again ReLU. And finally, we typically have a fully connected layer at the end, which produces the final output. But again, the fully connected layer is too heavy. That's the reason we maybe would have just one or two. ReLU and pooling are also are very fast, right? It's very easy to do that. And also ReLU and pooling could be integrated with convolution, as we will see later on. But the key point is that the convolutional layer is the most time taking. It accounts for 85 to 90% of the overall time. So that is why most of our optimization effort goes in the convolutional layer. So now if we take a look at the reference architecture for a CNN, here is what we have. So, I have not fully motivated this, neither do I want to motivate all of it right now, right? We should have something for the the later parts of the lecture. But the key idea is that given the fact that we have a lot of these parallel computations, we could have an array of processing elements that work more or less independently, as you can see. They are connected with an NOC, so there are row wise connections, there are column wise connections. You could have flexible connections also, in the sense you could have dedicated connections between these two. It doesn't matter. Each processing element is nothing more than a glorified ALU with a little bit of local buffer space. And then, of course, the NOC is connected to a global buffer. Think of this as the L1 cache and this as the L2 cache. And then it is connected to main memory on the memory side. And there is, of course, a brain of the neural network, pretty much, if you would say, which basically schedules all the computations. As we shall see, the brain is, quite important. And this is typically an out of order processor. So again, what I'm describing right now is something that I'm doing with insufficient background because we have not fully motivated this design yet. But it is important to keep this somewhere in the back of your thinking before we actually go forward, right? That you can have a sea of processing elements somehow connected, right, via an NOC. We could have a global buffer for global storage of values and local storage on each P, and an overall brain or an out of order processor to kind of orchestrate the entire communication. Now, coming back to our 7 loop structure, we argued that loops can be reordered, and the proof was essentially left to the brilliant viewers of this video by seeing that you already order them anyway, it doesn't matter, and the accesses are indeed parallel in the sense that the computations are indeed parallel, because there is no, as you can see in this loop, there are no dependencies, right? In the sense that for this, you just have to fetch an input value, multiply them, and add them. So, of course, this value is dependent on all of the input values that are, that lead to it. But again, those input values can just be computed in any order and just add it, right? So, only synchronization is that the addition needs to happen atomically, right? And I think we have studied a lot of that in chapter 9. But assuming that is taken care of, these are independent computations pretty much. But from a performance point of view, that ordering is important because it determines the order of accesses and consequently the memory locality and the memory performance. Right? So it determines the cache NOC memory behavior. That is why, from a performance point of view, their ordering is important. The next thing is that we have an additional option of tiling the loops. I'll just show it with code. So if you go back to loop tiling, we had discussed it in chapter 5, where what we do is that if a loop has 1,000 elements, we actually kind of divide it into two loops, where in one loop we kind of go in like blocks of plus 5, and then within the smaller sub loop, we go kind of iterate within the block. So the key advantage is caching actually. So if these block sizes are well chosen, then we'll kind of read it into the caches, do all our operations on them and write it back. So tiling is an important thing. And in case you don't know what is tiling, please go and look at the videos of chapter 5 of this book. So that is, tiling is explained in a reasonable amount of depth and detail over there. So if I were to tile, right, my 7 loop structure would actually become a 9 loop structure. And everything remains the same. The only modified lines are these two, right? So in this case, what we do is that in the previous case, we were increasing by +1, but we defined two new iterators h1 and w1, which go from 0 to capital H and 0 to W respectively. But in this case, they increase in every iteration by the tile size, which is th and tw. So we'll see that there are some advantages of doing this classic tiling. And then what we do is along with these 7 loops, we add two more loops. That's why it's a 9 loop structure, where we again introduce two more iterators H2 and W2 respectively to move within these tiles, right? So there are advantages in the sense that we are considering a tile, and pretty much for a tile, we are finishing its operations. So if the tile fits within the cache, then we read it once, do everything we need to do with it, and we are done. So we are kind of increasing the locality of the computation by considering tiles of size th cross tw, and we essentially fetch the tile, and then for one tile, as I said, we keep on fetching the rows and columns of the filter and keep on doing our convolutions and producing the output output pixels, albeit partially, output pixel values partially, right? So this is the classic advantage of tiling, something that we had seen extensively in chapter 5. So any of these loops in principle can be tiled, not once, but you can tile it several times. So it will only consider two-level tiling in this chapter. So as you can see, this is an example of two-level tiling where HW is kind of being divided into H1, W1 at the top, and then that is kind of strides of TH and TW, and we are iterating within the tile, which is basically here we are increasing by 1, right? We are moving within the tile. So the idea is that we need a method for formally represent the order of loops, because order of loops is not important from a correctness perspective, but it's important from a performance perspective. Specify tiling and also data locality, what to keep in these local buffers. Local buffers are these L1 caches, right? So what to keep over here, what is cached in the local buffers and what is not. So before I move to the formal notation, let me explain what I was meaning by the small error in the 7 loop code, and why it's a very small error, and why fixing it is no big deal. So the idea is that if this is the input feature map, we are kind of moving this kernel through, we are kind of sliding this kernel throughout. Issues will come at the right edge or the bottom edge. For example, assume your kernel is like this, or your kernel is like this. So let me maybe zoom in this part. So if I zoom in this part, your kernel would be like this. So these will be the valid pixels, these will be the invalid pixels. So in this case, what will happen is that when we are trying to read H plus R and W plus S, they will correspond to regions that are not valid, right? Because it is beyond the boundaries of the input feature map, right? And this would happen only at the right edge and only at the bottom edge. But taking care of this is very easy. Either we can tell our hardware that, look, kindly ignore all the accesses to these regions and just return a 0. Or we can explicitly zero pad the input feature map, in the sense we can consider a bigger input feature map, right? And store zeros in all these regions, right? So this is known as zero padding. This can be done. This is something which can be done, where it can be done kind of in software, where if your size is HW, actually take a larger input feature map, where actually on one side you add r minus 1 pixels, and other side you add s minus 1 pixels, and then pixels are essentially matrix elements, and then you just keep on adding zeros. So, or you tell your hardware that, look, if you get accesses in this region, kindly ignore and return a zero. So doesn't matter, you can match fix it in either software or hardware. In either case, it is fine. So let us now look at the formal notation. So in the formal notation, we have these 7 loops, right? So this code we have seen, but if you actually think about it, what is the information that we are capturing over here? We are essentially, the order of the loops is what is important. And as I have said earlier, reordering the loops makes no difference at all with respect to correctness, but performance is a different matter. So this entire piece of code can be represented like this, where we can say that this is just a sequential ordering of n, k, c, h, w, r, s. Why? Because that is the order of the iterators, n, k, c, h, w, r, s. So that is the order in which we are having our loops and doing our computation. So at least for a simple single threaded software implementation, this is good enough. So instead of having this entire piece of code over here, we could just have 7 of these symbols, where they all that they do is that they capture the iterators, and we could write them in this fashion, where this essentially indicates a sequential operator, which basically means that all of these loops are nested inside this loop. Similarly, all of these loops are nested inside this loop, so on and so forth. So this captures the sequential ordering of loops in single threaded software, right? That's the way we can interpret this, but this is a much more compact notation, which is far easier to analyze. So now let us work on this definition. So this is kind of more like, a definition where this basically tells you how to interpret these loops, in the sense they run sequentially, and everything within each sequential iteration is kind of captured. All of this is within one sequential iteration of an image. So if I have a n and then a parallel symbol, right, 2 bars after it, this basically says that we need to process all the images in parallel, or in other words, run a parallel for loop, which basically means that pretty much, if we look at software, we have not come to hardware yet. We will map it to hardware, but not now, not immediately. So in this case, we look at all of the n images, capital N images in parallel, right? This is what it says when I parallelize the iterator. What I can then do is, if I have 2 of these parallel, in the sense I look at all H in parallel and all W in parallel, pretty much both of these could be interpreted as process all the HW pairs, in the sense all the pixels of the matrix, that's what it's called. The elements are called pixels, in parallel, by mapping them to different, in this case, threads or P's, it doesn't matter. But conceptually, what you're saying is that for every pixel pair, map all of them in parallel, and for each, sorry, not pixel pair, coordinate pair, or for every pixel, do the computations parallelly and independently. This notation is interesting. Here, the only additional term that we have is this operator. This basically says that first we parallelize the loop with the iterator h, right? So first what we do is that we create groups of computations, where these groups themselves run in parallel, and then each one of them has a different value of the iterator h. Within each group, so these groups again, so each one of them is basically a separate group, and they run in parallel. But within each group, we map each of these values. Again, we process these values within each group. We process the W values in parallel, right? So the difference between this and this is that in this case, the ordering of pixels can be absolutely random, because as I said, all pixels are processed parallelly. So let's say if there are 100 pixels and we have 10 units, then we need to pretty much pick, uh, you know, 10 pixels, 10 more, 10 more, 10 more, and so on and so forth. And that can be done, in absolutely any order. But in this case, if it's a 10 cross 10 matrix, then what we would do is that we would create groups of 10 pixels. We would process the groups parallelly. And let's say if we just have 10 P's, then at one point of time we can process only one group. In that group, with the same H value, we'll process the pixels with the different W values in parallel. So this, in a sense, provides the finer structure of the parallelism. It's not as random as this. And it says how exactly we will do it by creating groups. And then inside each group, we could either process sequentially or in parallel. H dash and H dash dash, this basically means that H dash is the size of the tiles is incremented by the tile size th, and H dash dash is the iterator for accessing values within a tile. So if you remember in the tile loops, which I'll just take you back, we had the iterators H1 and H2. This is nothing but the same. So instead of H1 and H2, we have H dash and H dash dash. So of course, as I just showed, we could have execution folding, which means that let's say if we have more iterations, or let's say more pixels, the number of P's or threads, then what we can do is we can process a set of iterations, right? Process basically a set of pixels, a set of computations, right? So say computation in this case is an iteration of a for loop. Process the next set, so on and so forth. So now let us further complicate this representation of ours. So if I look at the tiled execution, so let me again go back to the tiled execution. This is nkc, this is h dash w dash rs, then h dash dash w dash dash. I mean it's not h dash, but it is like h and an apostrophe. But let me call it an h dash. So in this case, what we are actually doing is that this is capturing our order of execution. Okay, so it's capturing our order of execution. So it is basically saying that this is nkc h dash w dash rs h dash dash w dash dash, which is basically nothing but we have 9 loops, and the ordering of the loops is being captured with this. So we don't have to write the code or the loops or anything. This notation is good enough. Finally, uh, if you look at the following mapping, so let's look at this mapping. So these are, so as I said, all of these 7 terms have to be memorized. Otherwise, you will have a lot of difficulty understanding this. But I am proceeding with the assumption that the viewer of this video has memorized these terms. So in this case, we have NKC, the usual. And basically what we have is that the input IF maps are processed in parallel. Then we look at, for each IF map, we look at the pixels sequentially. And then we read in the filter. So the new thing here is the shaded box, which basically says that all the elements of the filter, right? So RS is essentially the kernel, the filter. These come from the local buffer or the L1 cache of the PE. So this is the material that is cached, right? It's cached locally in the local buffer. This is cached. So the idea here is to reuse this as much as possible, which basically means that I load in a filter, I use it, use it, use it, keep using it, and then basically then I kind of discard it to reuse it much later, or maybe if you want to maximize filter caching, then you have a filter and then you finish all the computations that would need this filter, and then you discard the value. So that would of course depend upon the structure of this notation. So we will go into the depth of it. But the fact is, the shaded box indicates that as per the context, the values that the iterators are fetching are coming from the local buffer, the local cache. So let us now focus on this caching business, right? So what exactly is cached, and how can we arrange our computations with respect to this caching? Because as I said, the ordering matters and the memory behavior matters, right? So it matters big time. So let us say that we have a weight stationary architecture. So we can have different stationary architectures, but let's look at one of the simplest. The weight stationary architecture, or the WS architecture, the idea is to reuse the filter weights as much as possible, right? We can parallelize the rest. And in this case, we don't care about hardware parallelization or software parallelization. Even though later on, I'll map these things to hardware, so you'll see how it is happening. But this is primarily from the point of view of software. But again, as I said, it doesn't matter. It's a conceptual device, right? So you can map it to any real substrate, be it software running on hardware like threads, or be it like a neural network accelerator, where, as I've shown, we'll have those B's, right? So it doesn't matter how we exactly do it. See, let's take a look at this notation over here. So let us say that all the filter weights are cached. And let's say you want to maximize the reuse. So if you want to maximize the reuse, what will happen? That you want to load them once, finish all the computations that require them, and then kind of discard these weights. So basically, the filter is dependent on two parameters, which is K and C, the output feature map and the input feature map. So what I could do is I could maximize the distance between this and this. So I could say that, look, first I choose a KC pair and finish all the computations with respect to that, which basically means that the filter, which is uniquely dependent on them, will get completely reused and then we will discard it. If that is the case, the structure of this notation will become KC. Then let's say we look at our images sequentially. Then assume we have some degree of tiling. So we process the tiles in parallel, and within each tile, we basically look at the pixels sequentially, right? So let us assume that this is the way we are interpreting it. Then what we will see is that this is of course a way of maximizing reuse, but in this case what would happen is that you would have to reload these images, in the sense that for every image, right, for every image over here, one input output feature map has to be processed, then reload the next image, then next image, right? So that's the way it will happen. That's not a very convenient way of doing things, because the point is that if this layer is somewhere in the middle of the neural network, and basically we need to basically send data for multiple images, then again change the KC, again send for multiple images, kind of complex. Ideally speaking, what you should do is that for a single image, just send it through the neural network, let it get processed. For the next image, send it through the neural network, let it get processed, so on and so forth. Don't mix images, makes life tough. So we can always have another kind of mapping and order of computation, where we parallelize on the basis of input output channels and look at images sequentially, which is something that would probably suit us more. So in this case, what we can do is we look at images sequentially, hence you have the sequential operator here. Then we basically parallelize our computation based on KC pairs. So they are mapped to different computational units. Within each, we take a look at the pixels sequentially and the filter weights sequentially, and the filter weights are cached. So of course, we don't have the kind of reuse that we have here, but this is somewhat a more convenient way of doing the computation, where we process one image at a time, parallelize the input output feature map space, in the sense do all those computations in parallel, And once you are a compute unit, you know your KC pair, then you just sequentially finish the 2D convolution. We could have other kinds of architectures. For instance, we could have an input stationary or an IS architecture. So in this case, what would really happen is that we could be processing images sequentially, one after the other. Then we could be processing our tiles in parallel. And then in this notation, as you can see, we are kind of fixing an output feature map, because the idea is we want to keep our input data stationary, right? So we fix an output feature map, and within that output feature map, what we do is that we slightly change the order of iterations here, and what we keep cached is this quantity, which let me kind of elaborate on this, right? That why are we keeping this cached? Where are we keeping it cached? And why is the order of computation this way? So in this case, let's look at this once again before we discuss stationarity at the end. So you process one image at a time. We are clearly distributing the tiles across the PE. So as far as the PE is concerned, this part is what is sequential, right? So here we are looking at one output channel at a time and sending the filter weights. So what is it that is we have cached? So we basically have the contents of the input tile for all the channels. So essentially for all the input channels, where I use the for all symbol, these are the contents of the tile that is mapped to the given processing unit, which could be a software thread or a hardware unit, we don't care. But for all the channels, we store their tiles. So, which is basically, if this is a tile for all the channels, we would store them like this in the internal cache. And basically, we would send it different filters corresponding to the output channel. And for all the output channels and their corresponding filters, once we have computed the convolutions, we would have the final output that corresponds to this tile. Because the final output for a tile is what? You take into account all the IF map, OF map pairs and their filters, do the convolutions, right? And then you add them. So you will get the final output for all the feature maps, right? Or let's say for all the output feature maps, or let's look at it in a different way. For a given output feature map, if we cycle through uh, the filter, so if the filter kind of moves through the tile, all right, and given the fact that the tile is cached, so basically what we do is that we take a few filter weights and make those weights kind of cycle through the tile. Cycle through basically means that you kind of multiply each element with the filter weight, and again consider newer filter weights and then multiply, so on and so forth. And finally, when you do the addition, this much, right, this part would compute the value the would compute the value of the tile, this particular tile, right, given by h dash and w dash, whatever it is mapped, in the output feature map corresponding to a given value of k. Now, when I look at many values of k, right, or let's say all the values of k, all the output feature maps for this particular tile given by h dash w dash would be computed by the unit to which it is assigned to. All right, so basically, this is kind of complex, but it's not that complex if you look at it several times. So the point is that we consider our computation an image at a time. We divide our input output feature maps or feature map space basically into tiles, and we parallelize it on the basis of tiles. So this part is kind of parallelized. Then a given tile is mapped to a computational unit, let's call it a P. Then what we do is that we cycle through the output feature maps. Now for a given output feature map, we perform this computation over here. In this computation, what happens is that we keep the values of, so this is the tile, right? So for this tile, for all the input channels, we keep those values cached, right? So all of this material is cached. What we simply read are the filter weights. So we read a couple of filter weights, they are sent over here. A convolution is computed. And the moment we have gone through all our filter weights, and then we compute the convolutions and perform the additions, etc. So essentially, we finish the computations of the loops. What we get is the H dash W dash tile of the output feature map that corresponds to a given value of k, right? Why? Because if for a given output feature map, you require to consider all the input feature maps, right? The corresponding tiles. Now, for each of these input feature maps, we multiply it with the corresponding filter, right? We convolve it with the corresponding filter, and then an addition is performed to arrive at the corresponding tile in the output feature map. So basically, this is not very hard, and of course, I'm not saying that this is the most optimal way of doing it. There are optimal, other better ways of doing it, as we shall see when we look at the section when this computation is mapped to hardware. But again, the key point is that we are clearly keeping part of the input tile cached in the P. And once the input tiles are cached, what is it that we have to send? We have to send the filter weights, right? So we have to kind of bomb it with filter weights because the input is cached. And then what is the output? Well, the output is the output map, the OF map tile, the corresponding OF map tile, or basically some part of it. I mean, at least partially computed OF map tile. So, of course, in this case, there is some amount of complexity. The complexity with an input tile is like this, that if this is a tile, right, and its size is th rows and tw, and we are doing a convolution, so then again we will have problems at the right edge and the bottom edge because the filter could be like this and these pixels will not be there. So what we do is that we can deliberately consider a bigger input map tile where of course there will be overlap across computing units, but that is unavoidable, where we extend this by r minus 1 pixels downwards and extend the columns by s minus 1 pixels. So then a tile size actually increases to th plus r minus 1 multiplied with tw plus s minus 1. And this is needed such that the worst case when your window is over here, right, when your filter is over here, then all the pixels underneath it are there in the cache. So otherwise there would be a need to communicate values across processing elements, these PEs, and that's hard. So we don't want to do that. So these values that which you would like to communicate, but in this case you are avoiding by deliberately considering a larger tile size, these are known as halo pixels, right? So halo is from the English word where it is kind of like that, this halo of light that comes when there is an occlusion. So pretty much is the same concept, but in this case these are known as halo pixels, and halo pixels have to be taken care of by, in this case, having a larger tile size, right? So that is how we are avoiding. So to come back, the sum total or the summary of our discussion is that if we are keeping a part of the input data cache, that is fine. In this case, the filter weights are what are going to be streamed through from memory, and the outputs will be partially computed unless we store the input tiles for all the channels in a processing element, right, in the local cache. Then we just bomb it with filter weights, and then compute the output tile actually, and we are done. So on similar lines, we could have an output stationary architecture. So in this case, we'll do the same thing. We'll stream through our images. We may have tiling. Even output stationary and tiling are orthogonal concepts. So you could have a non-tiled output stationary architecture as well. So in this case, what would happen is that we can parallelize the space based on the tiles. Then what we would do is that we would consider the computation one input channel, one input channel, then the next one, then the next one, so on and so forth. So in this case, the output data is being kept cached, right? So within the local buffer, the output data is being kept cached for a given tile. So what we could do is for a given tile, so tile is what? A tile is basically a set of coordinates starting from h dash w dash, right? So basically it is th rows down and tw columns. So this information for an output OF map is kept cached. So in this case, what we could do is that let us keep it cached for all the OF maps, right? This is what this would indicate, because the entire all the output iterators and for that tile everything is cached. So in this case, what we need to do is that we basically need to bomb this with inputs and filter weights, right? So then basically they will mutually get multiplied with each other and keep on updating the values of the partially computed output tile which is stored in the local buffer. And once we have sent all possible input channels and their corresponding filters, we would be done. Again, as I said, there are more efficient ways of doing this. We will look at it. But this is nonetheless one of the ways of doing this, where we tile the iteration space in the same way as we did. This is an analogous way as we did for input stationary. In this case, as you can see, just K and C have reversed their positions. So instead of KRSC, it is CRSK, right? KRSC, this is CRSK. They just reverse their positions. The logic is exactly the same. We keep KOF maps, not KOF maps, but KOF map tiles at the same position stationary. Stationary means cached in the local buffer. So we tile this iteration space in the same manner. Each PE computes all the OF maps for a given tile. We stream in the inputs and so on. And again, this issue of halo pixels will be there. And that has to be taken care of by deliberately having a larger input tile that is sent. So let us now look at a very different design. We call it the row stationary architecture. So let's look at the representing equation first. It's slightly different. And then I will talk about why it is this way. So what we do is that we do the same. We consider the data image wise, one image, then the next, and so on. Then we first look at a KC pair. So this we look at sequentially. So I'm considering a simpler avatar, but when we'll look at the hardware version, we'll also try to parallelize this space, but that, it doesn't matter. It doesn't matter at this stage. But essentially, fix a KC pair, which pretty much fixes the filter. Then what we do is this part is quite interesting. We actually make the division by rows. So what we do is that we distribute a row of the filter and a row of the input. So let's say a row of the filter and basically a row of the IF map. This is what is distributed to all the computational units, all the P's. And one P basically is in position of rows. So furthermore, what we can do, either we can distribute a single row or we can distribute tiles of rows, several contiguous rows. So I'm looking at the more generic case where we distribute tiles of rows, several contiguous rows. So pretty much to each PE, it will have a bunch of rows, a bunch of these input rows which are reasonably big, and a bunch of these filter rows which are reasonably smaller. So these tiles are the ones that are going to get distributed. right? So once that is done, and this is being done in parallel, then what we will see is that each P basically only needs to compute this much. If it needs to compute this much, let us focus on that. And what's a better way than basically getting rid of all the ink? So we do that and we focus on what a PE is supposed to do. So in this case, what it does is that it picks a row from the tile, an IF map row. Here you go. And it picks basically a row from the filter. And essentially, it assumes that so both of these are kept in the cache. Since they are kept in the cache, their corresponding iterators, right? H dash and R dash dash, basically saying that the entire IFMap row and the entire filter row are cached. So that is why we put both in a shaded box. So mind you, if I am permitted a small digression over here, inside the shaded box, the operators that are there, this operator doesn't matter. What matters is what are basically the terms. So in this case, we are kind of grouping them together. We could have also had two separate shaded boxes that would not have looked that good. But the idea of kind of grouping them together and putting them in a shaded box basically says that simultaneously we are caching a row of the IF map and a row of the filter. So both of these quantities, H dash dash and R dash dash, regardless of the operator between them, that doesn't matter. Both are there in the cache. So pretty much what the shaded box indicates is that it points to the iterator. And via the iterator, we go to the corresponding data that is actually cached. So essentially, it's trying to point to data. But as I said, or as I've argued earlier, if you're looking for pinpoint accuracy, this may not be the best way because you have to achieve a trade-off between accuracy and elegance. So here the idea basically is it's a row of the input and a row of the filter. And here a certain amount of contextual reasoning is important because you could also argue that it could be a row of the output with the input streaming in. So this is where the additional context is important, where we say that no, this is an IF map row and a filter row. So once they are cached, all that this part is doing is that it is basically placing the filter row pretty much at different starting points, which is what W does. And once it is placed at a given starting point, then the S iterator basically computes a 1D convolution between this part of the IF map row and essentially the filter row. So the key point of this part is that this is basically a 1D convolution, a one-dimensional convolution. And the reason that the row stationary architecture is very popular because as we shall see, the 1D convolution, the hardware for it is very fast. So we have ultra fast hardware for 1D convolution. So pretty much what we do is that we break all our 2D convolutions into a large number of fast 1D convolutions and use fast hardware to realize those. Right. So after the initial distribution, what we see is that each PE will basically compute the partial sums for a set of rows. Right. So that it is doing. And the way it is doing is that it caches a single row of the input and a single row of the filter, computes a 1D convolution, and then moves to a different row of the filter, caches that, and then computes a 1D convolution, so on and so forth. So after doing that, of course, the partial sums are stored. And as we cycle through all the input channels, at the end of this process, the entire OF map is computed. And again, we move to another OF map. So these values, partial sums, of course, have to be communicated across the P's and the final, computation has to be done. But how that is to be done We will look at it when we look at the hardware implementation of these algorithms. But at the moment, we are only talking at a high level, at a conceptual plane, where this can be implemented by both hardware and software. Hence, we have kept this discussion more or less simple. We have not gone beyond it. So, this lecture would end here. In the next lecture, we will discuss hardware architectures and how to realize, these representations or these equations with some modifications, of course, very efficiently on hardware, where hardware is basically an array of P's which read data from the local buffers, from the global buffer, and also pass data to each other, right? So there is a lot of data passing between P's. So how that happens is a topic of the next lecture. So now we will end here.